Hello! Today we will be discussing the different forms of electron clouds that electrons can take. It is important to understand that electrons are incredibly complex particles, and for a long time, scientists were unable to determine how they actually move. However, through calculations and a series of experiments, it has been discovered that electrons have a dual structure. They behave both as particles and as waves, exhibiting what is known as dualism. In order to represent electrons, we use specific symbols. It is commonly known that an electron is denoted by the letter E, and it carries a charge of -1. While the mass of an electron is very small, for simplicity, we often consider it to be 0. It is worth noting that electrons are typically represented by a symbol that shows their charge and designation. Additionally, the number of electrons within an atom is determined by its atomic number. However, electrons can also be divided internally based on their trajectory within an atom and how they move in space. This division allows us to categorize electrons as S electrons, P electrons, D electrons, and F electrons, each with their own distinct shape. The names given to these electron categories are derived from the spectrum lines associated with electrons. For instance, the designation of S electrons refers to a sharp boundary in the electronic spectra. On the other hand, P electrons are considered to be the main line in the electron spectrum, while D electrons are associated with a diffuse line, and F electrons are linked to the fundamental line in the electron spectrum. S electrons are represented by a circular orbit, and only 2 of these electrons can occupy a single energy level. Their representation is commonly shown with an S accompanied by the number 2 inside a squared box, indicating the presence of 2 S electrons. In summary, electrons exhibit a dual behavior and can be depicted using specific symbols. They are divided into different categories based on their trajectory and shape, such as S electrons, P electrons, D electrons, and F electrons. The names of these categories originate from the spectrum lines associated with electrons. S electrons, for example, follow a circular orbit, and there can be a maximum of 2 S electrons per energy level. Now, electrons are usually depicted not only in the form of a record in which quantum numbers, the principal quantum number or the orbital quantum number, are shown, but they are usually depicted in the form of quantum cells, and then electrons S are allocated 1 quantum cell, which is filled with arrows, where the first arrow is always pointing up and the second arrow will be pointing down. It is not possible to distribute the electrons in such a cell in any other way. It would be contrary to Pauli's prohibition. There's a rule that doesn't allow you to do that, and electrons are not placed that way. Now, if we are talking about P electrons have the shape of a volume 8, and such electrons are placed along the 3 axes X, Y, and Z. There are a maximum of 6 such electrons, and the notation that shows their maximum number would be P6. But these 6 P electrons, that is their maximum number, are distributed in quantum cells, of which there are only 3. Here is a reformulated version of the text with approximately 1183 characters. In each cell, the distribution of electrons follows a specific pattern. Initially, the up arrow represents the electrons' positions, and once all the cells are filled one by one, the electrons transition to the down arrow. Any other distribution method would contradict Gun's rule, which states that the electrons must be initially distributed in this manner. Furthermore, when discussing P electrons, each cell corresponds to a specific arrangement in space. For instance, the first cell corresponds to the x-axis, the second to the y-axis, and the third to the z-axis. Being able to identify which cell aligns with which axis is crucial for understanding the notation used to depict s and p electrons as outer level electrons. This knowledge becomes especially significant as it might be tested in examinations. Now let's delve into the topic of d electrons. D electrons exhibit 5 distinct shapes. So I'm not going to show all 5 of these forms, but I'm going to show just one of these forms that d electrons can have. They can have a figure 8 and a second figure 8 connected like this. That's one of the shapes, one of the 5 shapes. But there are actually 5 forms and they can be different from each other. There's a maximum of 10 of these electrons. And they write it down with a D10 record, and then 5 quantum cells are allocated respectively. 5 because 2 electrons will be filled in each cell. How do they fill up? And exactly the same way as we showed it for D electrons, for F electrons. These will be electrons initially located in the direction of the arrow up, and then when all the cells are filled one by one, then the arrangement of electrons will go down. So we have these, we have D electrons, and F electrons can have 7 different shapes. And then let's show one of these shapes. In fact, they are different. And one of the shapes, for example, of D electrons looks like this. But in fact, they are subdivided inside. Unlike S and P electrons, which cannot have any other shapes, D and F electrons can have different shapes. The maximum number of such electrons is 14. Then it is easy to see that the difference between each of the types of electrons is 4. Such an entry will be for 14. And again, this degree is read exactly as a number and not as an elevation to this degree. And we assign 7 quantum cells to the F electrons. And they're filled in exactly the same way as the D and P electrons. First, the electrons are distributed by the up arrow. And when all the cells are filled one at a time, all the quantum cells, then the electrons are placed downwards. If 2 electrons are present in a quantum cell, they are referred to as paired electrons. These electrons have the ability to react in chemical reactions, form bonds, and interact, although they do so reluctantly. On the other hand, when there is only 1 electron in a quantum cell, it is considered a valence electron. Valence electrons are more active and actively participate in bond formation with elements that possess unpaired electrons. Understanding which type of electrons are present in an atom is important, but equally crucial is understanding the order in which these electrons are filled in specific elements. In terms of electron filling, there is a set order that must be followed while filling electronic orbitals for elements. This order dictates which electrons belong to each energy level and determines the sequence of electron placement. At each energy level, the s electrons are always filled first. Until the s orbital of a given energy level is completely filled, no other electrons can be added. Once the first s orbital is filled, 2 additional s electrons are added according to their energy levels. Following the filling of s orbitals, 2 p electrons are added. This process continues until 6 p electrons are added. After the initial orbitals are filled, the next energy level begins with 3 s electrons. These 3 electrons must be filled before other electrons can occupy the remaining space in the energy level. Subsequently, 3 p electrons are added to this energy level. Only then do d electrons start filling in the subsequent energy level. However, contrary to expectations, d electrons are not filled immediately following p electrons. At the fourth energy level, the filling process starts with 4s electrons. After these 4s electrons are loaded, 3d electrons gradually occupy the available space in the energy level. And then after that comes the filling of 4p. And for example, in the fifth period, let's show also for the fifth period. The fifth period will start with 5s. Then the elements with 4ds will come next. And then come the elements that have 5p's. And so on. Then the question may arise, and when do the f electrons, which we have also shown to be orbitals, appear? Then we must remember that they do not begin until the sixth period. And it's filled in there, you get 4f's. And if we're talking about the seventh period, in this situation, the energy sublevel known as the 5f sublevel is occupied. These particular elements are typically found lower down in the periodic table, and they are referred to as the lanthanides. These elements belong to the sixth period, and their 5f sublevel is filled. On the other hand, the elements in the seventh period have their 5f sublevel filled, and are known as actinoids. However, regardless of the case, the electron configuration within an atom follows a strict order called the Aufbau principle. It should be noted that electrons always fill each energy level first, without violating this rule. The arrangement of s electrons, however, depends on the order within the period. That is how the electron configurations of atoms are determined. Understanding these principles will help differentiate and visualize the shapes of electron configurations. Farewell.